Everyone. I'm from the Advanced Light Source Synchrotron, and I'm providing the small angle X-ray scattering data of the same system. So thank you, Terry, for the nice introduction. Maybe I can just go next slide. Okay, great. First, to acknowledge our Beamline team, and particularly Feng Yu, who has been doing the analysis. I can't get the here. And then as well as all of our collaborators, including Guy in the audience. Okay, so in the next slide, I just want to get us all on the same page. Can you just push next slide? Okay. I just want to get us on all the same page. What is small angle X-ray scattering data? So it's kind of like if you take my hand and you think about my hand and you think about the bones in my hand, you can imagine that you can get a distribution of distances with that, and you can follow it very flexibly. And so in the same way, small angle X-ray scattering measures the distances between pairs of electrons, and we can do this in solution. And we take our sample and we look at the diffraction of X-rays as a function of intensity, as a function of the scattering angle. And so from this information, we can get the distribution of distances. So what does the experimental data show us about the protein A system? And is it a truly disordered linker or something else? And so here we collected data on both the wild type and the mutant, where we mutated the conserved linker. You can see the reciprocal space curves here. And then you can see that they're slightly different. And also we can do, similar to crystallography, we can do a Fourier transform and get the real space. This is the electron pair distances, and then this is the distribution of electron pair distances. So it's much more intuitive in real space. And so here's the wild type scattering pattern. The main part of the peak is showing the distances within the individual domains, but the orientation between the two domains are shown in these longer distances. And in particularly in the wild type, we see two shoulders indicating preferred distances. What was truly remarkable is when we did the glycine linker, you can see that those two preferred distances are significantly reduced, indicating that the wild type has a preferred distance between domains, and that the glycine linker now changes it, suggesting that there is some order within the disordered linker. So how about the prediction ensembles? Oops, sorry, went too fast. What we did is we took all of their models, we calculated SAXS curves, we then averaged them together, either using the given provided rates or just a simple average. We got an average profile of the entire ensemble, and we compared it with the experimental SAXS data, and we used a chi-square metric at this time to compare the curves. So when we did this, what we saw was here is the each group, and then the chi-square fit to the wild type data and to the glycine linker. And you can see that there's generally good fit between when a group is good, they're generally good for both things. And then we then did a combined score where we combined both scores, and we took a closer look at the two top models, two top groups, the Lindorf-Larsen and the MoMA team. So when we take a closer look at these individual groups, what we can see, here is the wild type data, here is the glycine data. You can see that they do an excellent general fit between the those two, although we give the caveat that they were provided the crystal structures of the two domains. But when you take a look at the residuals, which is the difference between the model data and the experimental data, you can see that there is significant bias in the residuals, indicating that they were not able to really replicate the experimental data. This may be also obvious in the experimental data, where in the real space data, the 308 showed that they had preferred distances, but they had preferred distances in both the wild type and the glycine mutant, and also their preferred distances were slightly off, which is visible in this residual. They weren't able to get the exact identical preferred distances that we see in the experimental data. The errors are indicating where the experimental data peaks are. The Lindorf-Larsen did a better job with the glycemine. They had a much smoother curve, but they also had a smoother curve for the wild type protein. So neither team was able to capture the difference between the wild type and the glycine mutant. So just so that you have a feeling for, well, how can you capture that? What we did was we took the crystal structure and mimicked what we could pick up as a good fit. And so each of these each color is represented here in the pair distribution function. So for example, the pink is shown in the purple line, the red here is shown in the red line here. And that shows you the impact of the orientation and distance of these two domains relative to each other. This is in black dotted lines is the experimental data. And when we do an ensemble of all these structures I showed you, you can see that the ensemble does a pretty good job of fitting the experimental data. However, this ensemble of structures that we made up do not match the RDIC data that Terry was speaking about, indicating that perhaps we have a concern in small angular X-ray scattering whether or not we can accurately match what is occurring in solution, whether we have the resolution. And so I want to end my talk by talking about, with the conclusions from this. And one is that I think we showed that SAXS showed that the wild type has preferred distances between the domains despite having a flexible disordered linker, but loses those preferred distances with an all glycine linker. And so here's some thoughts about our for CASP is that small angular X-ray scattering does not have a singular ground truth, making it very difficult to do a comparison with atomic models. And also, SAXS can capture this relative preferred distances, but it's quantitatively difficult to measure differences on such a subtle feature of the curve. And so we really need to get good scoring methods of combined reciprocal and real space to capture this information. And one thing that I pull out to the mathematicians in the audience is that we have no community recognized methods for real space comparison. And so we've been working with that, and many groups around the world have been working on that and have not been successful. And finally, to speak to the uniqueness of the SAXS solution, that perhaps we will need to combine with the NMR to see with the SAXS data for better modeling of the flexible region, and also to test if SAXS can distinguish NMR RDC compatible models with our randomly generated set of models. And I leave you, with this set of questions, and which will be in part discussed in the question discussion section. Thank you. I'm done. Did I catch us up a little bit on time?